Okay, let's talk about dilutions. I'm just going to start reading the slide. Often we are given a solution that is more concentrated than we need. This is true in industry, in hospitals, in labs. We are constantly having to dilute things. And when you order a solution that is more concentrated than you need, it's called a stock solution. So to get a solution that you can use for a patient or whatever it is, you have to dilute it oftentimes, and this is called your working solution. Now the question then becomes right here, how do I know how much solvent to add to get the concentration I need, and how much of my stock solution do I need to take as well? So there's a kind of two questions here. How much of our stock solution do we need, and how much solvent do we add to that to get the concentration we need? And there's a very simple equation for these problems. It will remind you a whole lot of Boyle's law and the gas laws. But instead of P1V1 equals P2V2, we have M1V1 equals M2V2, where M is the molar concentration. Remember, this is moles per liter. And volume can be in milliliters or it can be in liters. So just because you have liters over here in molar does not mean you have to work the whole problem in liters, as long as your units on V1 and V2 match. So if they're both milliliters, great. But if you have 1 milliliters and 1 in liters, you're going to get the wrong answer. Okay? So let's actually look at a couple of these. Essentially the way these work, you have 3 of the 4 pieces, and you're going to cross divide in some regard to solve for the 4th piece. So here it says I have 75 milliliters of 3.5 molar glucose. So this is our initial, I believe, M1 and V1. Then it says you dilute to 450 milliliters. So this is definitely V2, this is definitely V1, and this is your initial concentration. Then it says what is the new concentration? So you're solving for M2. So we're just going to plug these in. M1, 3.5 molar times 75 milliliters times V1 equals M2. We don't know that. We're looking for it times 450 milliliters. So to solve for M2, we are going to cross divide both sides by 450 milliliters. And that cancels out on the right side. So then the problem becomes 3.5 times 75 divided by 450. You should get 0.583 molar. That is M2. And remember, this is moles of glucose per liter of solution. If you had to define that, you would need to know that. Whoa. Okay. So that's an example of a dilution problem. Another one we can work really quick. It says you can buy 1 molar NaOH. So this is definitely M1. I need 750 of 0.32 molar NaOH. So this is definitely M2. How do I prepare this? Now, question here, is this V1 or is this V2? It's the only volume given, and it's not asking you what is the initial volume you need to take, or the question is how do I prepare this? So you have to say, what is this volume associated with? This volume is associated with this second concentration. So this is V2 because it is associated with your new or your working concentration. Okay, so be careful. Just because you're given one volume doesn't automatically mean it's V1 in the problem. Make sure you read it and understand that. Now we'll plug these things in. So we're solving for V1. So we know M1 is 1 molar times V1. So M1, V1, we're looking for V1, equals M2, which is 0.32 molar, times V2, which is 750 milliliters. So we'll divide. It's late. Both sides by 1 molar. And our problem becomes V1 equals 0.32 times 750 divided by 1. 0.32 times 750. And I got V1 is 240 milliliters. So what you would say, how do you prepare this? You would say you take 240 milliliters of your stock solution, and you dilute it to 750 milliliters. Okay. Let's talk about electrolytes. Electrolytes are the kind of the biology word for the chemistry term ions. So electrolytes are ions. They are ions dissolved in solution, and they're called electrolytes because that solution can then conduct electricity. Now, once ionic compounds are dissolved into ions, we don't talk about the compounds anymore. We just talk about the ions, or the concentration of ions. And this is exactly how we see blood, right? We don't say, well, we have this much sodium chloride in our blood. We say we have this much of chlorine or chloride. We have this much sodium in the blood. We talk about them as electrolytes, individual ions. And just to illustrate that point a bit further, let's say we have two little setups like this down here, 1 and 2, and we're going to put different compounds into the water, and we're going to make solutions. So you can see we have sodium chloride and potassium bromide for one, but then we have two different compounds, sodium bromide and potassium chloride for the other. But when you put them in solution, what happens? You'll get sodium, you'll get chloride ions, you'll get potassium, and you'll get bromide ions. Well, what will happen over here? You'll get sodium ions, and you'll get bromide ions, you'll get potassium ions, and chloride ions. And if you look at these two solutions, all these ions floating around, they're exactly identical. If you put the same concentrations of these compounds, you get the same concentrations of these ions. So, another thing about electrolytes is you have strong, weak, and non-electrolytes. What's the difference here? You have some things that will completely ionize, meaning they will completely dissolve, and at the end of that process, you will have no more of the original ionic compound. You will have just ions, and that is what we call a strong electrolyte. So this is indicated here in the picture with a single arrow pointing towards the ions. Okay, we started with sodium chloride as a solid, the ionic compound, and you end up with all ions. No compound left over. All right. A weak electrolyte, on the flip side, is one that you will have some of the original compound left over. So, for example, acetic acid, CH3CO2H. This is acetic acid. It will dissolve and give you acetate anion, and the hydrogen ion. But then those two things can recombine and make more acetic acid as well. It's a weak electrolyte because, and it's represented by this double arrow here, indicating that you'll have both in solution, not just ions and not just your compound. That's a weak electrolyte. Now, a non-electrolyte is something that doesn't make ions. It will dissolve. Okay, it will dissolve. Glucose, if you have a big solid piece of glucose, let's say we have a bunch of glucose molecules. I'm going to draw a picture of this. All these little red spheres are glucose, and as a solid, we know this is how a solid looks. All of the particles just arranged together. And let's say you dissolve it in water. Well, what's going to happen to those particles? Now they're all aqueous, and it just look like this. They'll just be spread apart, and they'll be moving past one another because that's how things behave in a liquid phase. Okay, so all of these are glucose, individual glucose molecules, but none of them are ions. There's nothing charged here, so no ions on the product side. So this is a lot of biological molecules behave this way. They are non-electrolytes because they don't make ions, but they do dissolve. So make sure you know the difference there, and make sure you understand that and could convey that on a test. So I had a lovely poll question if we would have been in person, but look at these three, and I'd love for you to pause the video and then quiz yourself. Which one's a strong electrolyte? Which one is a weak electrolyte? Which one's a non-electrolyte? So if you've done that, we will look at these. Number one, you have a double arrow, so it's definitely not a strong electrolyte because you'll have both the original and you'll have some ions. So, we have a typo here. This should have a minus sign on it. So you do get ions, But you also have some of your original compounds. So this is by definition a weak electrolyte. What about the next one? Insulin. You have a double arrow, so insulin will dissolve, but on the product side, we have no ions. Okay, insulin is not charged. We have no charge here. We would, if you saw something right here, if there was a plus or a minus, then you would have an ion, but we have no ions. So that means it is a non-electrolyte. And then on the last one, HCl, we have a single arrow pointing towards all ions. So this means it is a strong electrolyte. Okay, so make sure you can convey the difference between these things